Okay guys, in this video we are going to be doing some calculations of entropy changes for specific processes. Here on this first slide I've got a number of formulas. First up is the general formula for calculating an entropy change. Okay, so this one is always true. For the system you need to consider an equivalent reversible process, and then you would integrate the infinitesimal heat divided by the temperature. If you are considering an adiabatic reversible path, the entropy change is zero because the heat is zero. Or if you're considering a cyclic process, that is, the initial state is the same as the final state, because the entropy is a state function, the change in the entropy is equal to zero. We looked at that in the last video. We have already explored isothermal ideal gas expansions, and so this is the formula that we came up with previously. If you're given pressures instead of volumes, you can just use the ideal gas law to substitute in for the volumes and express the formula in terms of the pressures. Notice the minus sign out in front, and that's because volume and pressure are inversely related. This diagram shows, it's essentially illustrating that last formula. If you plot delta S in units of N divided by R as a function of the ratio of the volumes, you see this logarithmic increase in the entropy change. So the bigger the volume change, the larger the entropy change. Here in this problem, we are asked to do a couple of calculations. So first off, they want us to calculate the entropy change, the molar entropy for a perfect gas expansion when the gas volume is doubled. That's fairly easy to do, so we use this formula. In this case, the final volume is double the initial volume. This is the reversible path that we're considering, so it's already built into the formula. It's 1 mole of gas, so we're going to have 8.314. That'll be joules per Kelvin per mole, and then that's multiplied by the natural log of 2 to get the number that they want. And so I'm getting 5.76 joules per Kelvin. And we'll go ahead and put per mole. So that's for every mole of gas that's being expanded. In the follow-up problem, it's a little bit more complicated because they're asking us about the surroundings. Okay, so they want us to calculate the change in the entropy of the surroundings and then calculate the total entropy change, so that is system plus surroundings, for two different paths, the reversible path and the expansion under free expansion with zero external pressure. So for part A, let's start with the surroundings. So the delta S for the surroundings, okay, for a constant temperature process is going to be equal to the heat that the surroundings experiences, the real heat, not a reversible heat, the real heat, divided by the temperature. Now, the surroundings heat is going to be equal and opposite to the system heat. And for an isothermal process involving an ideal gas, delta U equals 0, and heat is going to be equal to minus the work. And so for a reversible gas expansion, we've already studied the work. It's going to be negative nRT, natural log Vf over Vi. We're dividing by T. Those cancel out, and we see that for the reversible path, delta S of the surroundings equals minus delta S of the system. Okay, so it's the numerical value will be minus 5.76 joules per Kelvin per mole. The total is going to be the system plus the surroundings, and for this reversible process, that's going to be 0. Let's look at the free expansion. For the free expansion, everything we've written down is the same. That is delta S of surroundings equals work divided by temperature. But in the case of a free expansion, work is equals 0. And so we get that the entropy change of the surroundings is 0 in this case. And so the delta S for total will be equal to the minus 5.76 joules per Kelvin per mole. So for the system, you always have to use the reversible path, right? Notice that delta S for the system is the same for both parts A and B. You have to use this, whatever the reversible equivalent path is. But for the surroundings, you use the actual heat of the process. In part A, we used the reversible heat, which is equal to minus the reversible work. In part B, we used the real heat and the real work, which were both 0 in this case. Well, on this slide, I present the formula for calculating the entropy change of a phase transition. Phase transitions are usually carried out isobarically, in which case, and it's isothermal. The phase transitions occur over a constant temperature. And so delta H is the heat for the phase transition divided by the temperature of the phase transition. In this table, we're looking at different substances. We've got their freezing point. We've got their, we've got what it lists are the, these would be the entropies of fusion. These are the entropies of vaporization at the fusion temperatures and at the boiling points. This slide shows enthalpies of vaporization for different liquids, the different boiling points, and the entropies of vaporization for these different liquids. Notice that a lot of the liquids, they have very similar entropies of vaporization, close to about 85 joules per Kelvin per mole. And that observation is the basis of what's called Troutmans Rule. It's an observation that the change in entropy associated with vaporization for many liquids is about 85 joules per Kelvin per mole. We're being asked to use that to estimate the enthalpy of vaporization for bromine. So we'll take the formula for calculating the entropy of vaporization, and we'll rearrange it and solve for the enthalpy of vaporization. We need to evaluate the boiling point in units of Kelvin. And we'll multiply by that 85 joules per Kelvin per mole. And so I'm getting 28.2 kilojoules per mole as our estimate for the enthalpy of vaporization of bromine. And I'll let you look it up to see if it's any good. On this slide, we've got, these are the formulas for calculating delta S for heating problems. So if you're heating up a gas, you could heat under isochoric conditions or under isobaric conditions. For isochoric conditions, the heat is CV dt divided by temperature. In many cases, the heat capacity can be regarded as a constant. So the CV comes outside, and then you're integrating dt over t, which gives you the natural log of Tf over Ti. If the heat capacity is not a constant, then you have to explicitly do that integral. So sometimes the heat capacity will be given to you as a polynomial. You need to take that polynomial, which is a polynomial of temperature, divide by temperature, and then integrate the terms to get the delta S. For isobaric conditions, the case is similar, except that the heat is given by Cp dt rather than Cv dt. And so, again, if you can regard Cp as a constant, you can pull it out of the integral, and then you integrate dt over t, which gives you this factor here, and then you're good to go from there. So this is a plot of these two formulas. It's a plot of delta S as a function of the ratio Tf over Ti, where it could be either Cv or Cp. Anyway, what you're looking at for the different curves are different values of this heat capacity. And so what you see is the logarithmic increase in delta S as you increase the ratio of the temperature difference. So the bigger the difference which you heat the gas, the larger the increase in the entropy. And so here we have a problem where we will put this into practice. So we're being asked to calculate the molar entropy change for heating water from 20 degrees Celsius to 50 degrees Celsius. I guess we'll assume that this is an isobaric process, so it's isobaric heating. Assume that the constant pressure molar heat capacity is constant, 75.3 joules per Kelvin per mole. And so the delta S would be, per mole would be Cp m natural log of Tf over Ti. And so we'll have 75.3 joules per Kelvin per mole, natural log of 323 divided by 293. So I'm getting an entropy change of 7.34 joules per Kelvin per mole. And if you had 5 moles of gas, you would multiply that by 5. Right? So you can always, to get the non-molar version, you would take the number of moles and multiply by the molar entropy change. What do we have next? We've got another example problem here. This one, we've actually got two types of changes going on simultaneously. They want us to calculate the entropy change when we expand argon from 0.5 liters to 1 liter, and we simultaneously heat it from 25 degrees Celsius to 100 degrees Celsius. Well, the nice thing about doing calculations with state functions is that they are independent of the path, and so we can simply break this problem up into two parts. One part will be expanding the gas isothermally, and then the second stage will be heating the gas at constant volume. And so the two terms just simply add together. So we'll have one term for the volume change, and then we're going to have a second term, which will be, we'll just do NCVM natural log of Tf over Ti. So we've got 1 mole. Let's just assume 1 mole. It's not explicitly stated, but we'll just assume 1 mole. Natural log of 1 over 0.5. So that's the volume term. And then for the heating term, we'll have 1 mole of gas. The heat capacity for argon is going to be 3/2 times 8.314 joules mole Kelvin. And then it's the natural log of, let's see, that would be 373 Kelvin for the final temperature divided by 298 Kelvin for the 25 degrees Celsius. So we've got 2 parts here. So this first part, we've actually calculated it already. It's 5.76 joules per, I guess this would be per Kelvin, since we've got the moles in there explicitly. And then we'll do the second part. This one's giving me 2.80 joules per Kelvin. And then we add those together. So I'm getting 8.6. We'll do 8.56 joules per Kelvin. So that's our answer for that part. Well, I'm going to go ahead and stop this video here, and we'll pick up with measuring entropy in the next one.